Okay, so we start with problem 8, which is essentially converting things into uh, either numbers or trigonometric values into e to the I beta, or simplifying them pretty much. So we started with a, which is just 1, and now 1, of course, 1 is e to the I times 0, because which equals e to the 0, which equals 1. B, so sine beta minus I cosine beta to the power 11. Now notice that e to the negative I beta is cosine beta minus I sine beta. This here, the sine and cosine are reversed. So I substituted in the identities for sine and cosine and simplified. So here we multiplied I and the numerator and denominator of this fraction. So then the e to the negative I beta is canceled right here. And then you just get 2 e to the I beta over 2i to the power 11 equals e to the I beta over I to the power 11, because the 2's cancel right here, which is just e to the 11 I beta over I to the power 11. C, we started with 1 over square root 2 over 2 times cosine beta minus I sine beta cubed. So we simplify the fraction of the denominator. We then substitute e to the negative I beta for the cosine beta minus I sine beta. So then we and since e to the negative I beta is in the denominator in this fraction, we move that to the top as a positive exponent. So 2 over square root of 2 e to the 3 I beta. D, I didn't have room for the start of the problem, but it was square root of 3 over 2. That's the cosine. And this is a minus I times 1 over 2 sine beta, and all to the power 7. So we simplified. The i's cancel in the denominator sign and the I in front of it. Those cancel. The 2's multiply out. So we have 1 over 4 times, and then we essentially group like terms. So square root of 3 minus 1 times e to the negative I beta comes from this term and this term. So we group those like terms. We simplified out the negatives. It's still the power 7th, and then we distributed the 7th power. So it's 1 over 4 to the power 7 times the whole square root of 3 minus 1 to the power 7 times e to the 7 I beta plus square root of 3 plus 1 to the power 7 e to the negative 7 I beta. Okay, so for 28, we were essentially showing that this transformation works. For this rectangle, we're transforming it through f equals e to the z as a half circle. So what we do is we consider the line segment x equals x sub 0 inside S. Now points in that segment have the form z equals x sub 0 plus iy, where 0 is less than or equal to y and is less than or equal to pi. Now, for these z, e to the z equals e to the x sub 0 times e to the iy equals e to the x sub 0 times cosine y plus I sine y. Now the cosine y plus I sine y makes a semicircle, and the e to the x 0 is the radius of the semicircle. Now, so when you have x sub 0 is 0, you get e to the power z equals e to the power 0 equals 1, so it's just cosine y plus I sine y. When x is approaching negative infinity, you get e to the power x sub 0 approaching infinity, but doesn't touch infinity, so you have the whole x 0. But it fills in the semicircle.
We're doing problem number 34 for section 1.5. Our goal here is to linearize this in the middle, cosine beta to the 5th, and then solve the integral of that. First and foremost, what you're going to do is you're going to take cosine theta to the fifth, and you're going to substitute in the identity, which is e to the I theta plus e to the negative I theta over 2. Then you're going to take that amount on the inside to the fifth power. However, seeing as we have limited space on the board, I did the first step here of how that's going to go, just to show you the process. E to the I theta plus e to the negative I theta over 2 times e to the I theta plus e to the negative I theta over 2 equals e to the 2 I theta plus e to the negative 2 I theta plus 2 over 4. You carry that out, all the steps in the middle of multiplying this to the fifth, and you eventually get e to the 5 I theta plus e to the negative 5 I theta plus 5e to the 5 I theta plus 5e to the negative 5 I theta plus 10e to the I theta plus 10e to the negative I theta over 32. Your next step would be to break up the different components of that so that we can eventually substitute in for our identities. We've got e to the 5 I theta plus e to the negative 5 I theta over 32 plus 5e to the 3 I theta plus 5e to the negative 3 I theta over 32 plus 10e to the I theta plus 10e to the negative I theta over 32. We substitute out 16 there. We'll get 1 over 16 times e to the 5 I theta plus e to the negative 5 I theta over 2 plus 5 over 16 times e to the 3 I theta plus e to the negative 3 I theta over 2 plus 10 over 16 times e to the I theta plus e to the negative I theta over 2. We can substitute in now. So I'll have 1 over 16 times cosine of 5 theta plus 5 over 16 times cosine 3 theta plus 10 over 16 times cosine theta. Now that we have this, we can actually go back in and integrate. So we have the integral of 1 over 16 times cosine 5 theta plus 5 16 cosine 3 theta plus 10 over 16 cosine theta d theta. We can, using integral rules, go ahead and do 1 over 16 times the integral of cosine 5 theta d theta plus 5 over 16 times the integral of cosine 3 theta d theta plus 10 over 16 times the integral of cosine theta d theta. And eventually we'll get the solution of 1 over 16 times 5 sine of 5 theta plus 5 over 16 times 3 sine of 3 theta plus 10 over 16 sine of theta plus c. Because as is a rule, the integral of cosine is sine, and since there's a number on the inside of there, it's going to be divided by that, so it would be 1 over alpha sine alpha theta is the form. And eventually we get 1 over 80 sine of 5 theta plus 5 over 48 sine of 3 theta plus 5 over 8 sine of theta plus c. That is our answer to the problem.